Today we're going to look at the chi-square test of association or independence. Mechanically, this test looks like a test of homogeneity, but the tests are quite a bit different. They have different purposes, they have different designs under which the data are gathered, they have different hypotheses, and the interpretation of the results are different. The purpose of this test is to test the null hypothesis of no association between two categorical variables in one population. The conditions are the data are counts, the data come from a random sample, all expected counts are greater than or equal to 5, and the sample observations are independent. The chi-square statistic is the same as it is in all the other chi-square tests. The sum of the observed minus expected count squared divided by the expected count for each category or each cell, in this case in a two-way table. The expected counts are calculated by multiplying the row total times the column total divided by the table total, and the number of degrees of freedom will be equal to the number of rows minus 1 times the number of columns minus 1. On your calculator you can find this test at Stat Test C, chi-square test. This is available on both the TI-83 and the TI-84. You're going to have to put your observed counts into a matrix first before you run the test, and then the calculator will find the expected counts, degrees of freedom, chi-square, and p-value for you. Here's an example of how this works. A researcher in a small state wants to see if political party affiliation and gender are associated. A random sample of 202 registered voters in the state yields the observed count shown in the table below. Do these data provide evidence of an association between party affiliation and gender in this state? You can see we've got gender broken down into categories of male and female, and party affiliation broken down into Democrat, Republican, and Independent parties. And the observed counts are the large numbers in each cell. We've calculated the column totals for each column, calculated the row totals going across. The table total is 202. The expected counts are in parentheses, and I'll get to those in a minute. The null hypothesis is that the party affiliation and gender are not associated, versus the alternative that they are associated. Now, if they're not associated, you would expect 105 out of 202 times these 84 Democrats to be in this cell right here. So we've got 84 Democrats total, and 105 202nds of them should be in the male row. And all the expected counts are calculated that way. It just amounts to multiplying the row total by the column total divided by the table total. I got all of these off the calculator when I ran the test. The conditions are the data are counts by inspection. The data come from a random sample as stated in the problem. The expected counts are all at least 19, which is greater than 5, and the sample observations are independent since the population is much larger than 10 times the sample size. When I calculated the chi-square statistic, I got 4.85 for the value of that statistic, and the degrees of freedom are 2 minus 1 times 3 minus 1, or 2, and the p-value is about 0.0884, and that's not small enough for me to reject the null, so I failed to reject the null hypothesis that party affiliation and gender are not associated. These data do not provide evidence of an association between party affiliation and gender in this state. Now, since the test of homogeneity and the test of association are so much alike in terms of how they work mechanically, it's a valid question to ask, how can we tell these two tests apart? The data usually come in a two-way table in both tests. The chi-square statistic, degrees of freedom, and expected counts are all calculated in the same way. So what's the difference? Well, in the homogeneity test, we have one variable and two or more populations. And you'll often see this test in the context of randomized comparative experiments, where a group of experimental units are randomly assigned to treatments that artificially sets up two populations, or perhaps more, depending on how many treatments there are. And the one variable is maybe the degree of success or relief that somebody experiences, say, in a clinical trial. In observational studies that use this test, the different populations will usually be fairly recognizable. They might be groups of people from the same locality. spaced apart by a number of years or something like that, or they might be completely different groups of individuals from different localities. It can take on a lot of different forms, but you generally will recognize the different populations, and you'll have an independent sample taken from each population. And when you read the problem, you can usually tell if there's an independent sample being taken, and that would give you a hint as to the fact that you have more than one population. In terms of the wording of questions, look for words like this. Is there a difference in groups, or is there a difference in distributions of a variable? Those usually indicate that we're trying to do a homogeneity test. But really what it comes down to is the design under which the data are gathered. Do we have independent samples for each population, or do we have random assignment to treatment groups? That usually is what is the key factor there. In an association test, we have two variables in one population from which we draw one sample. So you can tell from the design that one sample has been taken and then categorized according to these two variables. This kind of test usually appears in observational studies. Look for language about two variables being associated or related or independent. If you see those terms, it's usually a hint that it's a test of association that we're trying to do. But again, it all comes down to the design under which the data are gathered. That is really the key thing, which is what we're going to be able to use to tell those two kinds of tests apart.